to lecture 79. So, today we are starting for the 10th week, and we are going to discuss about the trajectory transfer. So, the trajectory transfer it can be coplanar, it can be non coplanar, it can be interplanetary, it can be on the same planet. Okay. So, we are first going to discuss all these aspects, what does mean by trajectory transfer and where do we apply. Okay. So, let us start with trajectory transfer is designed as change in orbit through change in velocity usually by application of an impulse. Often one or more trajectory transfer maneuver may be required. Sometimes it may be 2, sometimes it may be more. So, in general you will see that a minimum of 2 is required, but just say you want to throw a satellite out of the satellite orbit into the space, getting it lost. Okay. So, one impulse can be enough in that case. But in general, if you are doing the earthbound satellite maneuver, so minimum of 2 impulse for one trajectory transfer it is required. So, as we have discussed earlier that once we launch the satellite, so we inject it into the orbit somewhere. So, here v is the velocity vector imparted to this. Say this is the perigee position. So, true anomaly will be measured from this place. And then the satellite will coast to complete the orbit, it will go all the way and then come back like this. It is not a good figure, but I can make another one. So, here in this case, if I take this as an ellipse and at the center, at the focus of an ellipse, I have the earth and this is the perigee position, and somewhere from this station the satellite is being launched. So, it is injected in the orbit here in this place. So, at this point it will become tangent to this orbit. And this is your theta, the true anomaly. So, this is the injection point, v 0 is the initial velocity and r 0 is the So, already these issues we have discussed earlier. So, once you have injected, so this is the orbit in which the satellite is. This is a very distorted figure, remember, because the earth radius is 6400 kilometers and we have written as 6371. This is the average value, or 6378 the equatorial radius we have used. Okay. So, say roughly the 6400 kilometers. So, if you are launching the satellite in 250 kilometers orbit at the altitude. So, this distance is your from here to here 250 kilometers. So, it will be a very small thing, it will look something like this, only if you look on the scale. So, it will be very close to the surface, but for clarity I have expanded it. Okay. So, this is the earth. So, once the satellite is injected, so this is not the orbit in which you are looking for. This is the altitude, say 250 kilometers, or maybe at this point your altitude is 250 kilometers. At the perigee position it will be the least. Okay. So, either here or either here, whatever it is. So, that we have to compute where the perigee will lie, and that depends on the theta value, theta 0 that we have to estimate, and we have done it earlier in the orbit determination process. So, thereafter as earlier also we have discussed that this perigee needs to be raised 250 kilometer. If it remains here in this place, so slowly this orbit will decay, it will start decaying and the orbit will move into the atmosphere as it loses energy. E prime we have written as mu by 2 a. So, as your E prime is the total energy per unit mass. So, as E decays, okay, so A will become smaller and smaller, so that it becomes more and more negative. So, the first maneuver required, say this is elliptical in nature. So, the first maneuver required will be here in this place, you impart delta v velocity here, so that this is raised. So, immediately the lowest altitude has to be raised. Okay. So, if you impart velocity, it will go up. So, from here this position will remain unchanged and this position will come here in this place. So, this way your orbit then it will look like something this way. So, this is the change orbit. Now, it has come to this place, then you may like to raise this one. So, then you give impulse here in this point by delta v. So, this point will be raised. So, this way you can circularize the orbit, or you can make it elliptical, you can increase the altitude or you can decrease the altitude, it depends on the your requirement. So, these issues we have discussed earlier also. So, in general, why the trajectory transfer is required? Trajectory transfer is required. Why the trajectory transfer is required? Reason can be the orbit in which you have launched, this is not the desired orbit. So, satellite may not be in the desired orbit, and it requires maneuver. So, needs to be transferred or needs to be put into a put into the proper orbit. sometimes we want to achieve certain mission and then another mission. In that case, trajectory transfer is required. Not only this one, but also the launch station does not allow to put the satellite in the desired orbit. And therefore, change is required. And this especially happens in the case of the India. If you see, the India is located here, and here the Bangladesh and other countries are there, and your SAR is here in this place. Okay. So, satellite is you want to launch a satellite in the equatorial orbit, say you want a geostationary satellite and this is the equatorial orbit, but the launch station position is somewhere off of this. Okay. Thereafter, you are also interested in launching the satellite. So, this launch station, ground station position, it does not allow to put it into directly this equatorial orbit. So, first what you will do, you will launch in certain other direction. Okay. And also you have to save other countries, so that in the case of rocket fails, it does not fall over the populated area. So, say you are launching along this direction, and so this is not a proper direction, you need here in this direction. So, this is the desired direction, desired orbit direction, and therefore, from this orbit to bringing it to this orbit, we require some extra impulse to be given. So, if you give extra impulse here in this point, okay. So, here initial velocity is given here in this direction, this is V I and this is V f. So, this is delta V equal to V f minus V I, this is the impulse required. So, if you give impulse like this here in this direction, okay. So, this velocity vector will change to this velocity vector, and thereby your satellite orbit will change. Okay. So, this way you will not only you can change the A, E, I etcetera, but also the nodal angle can be changed, the argument of perigee can be changed, and obviously theta is the true anomaly. So, this is also done in the same orbit, you can change the value of the theta. So, in that case, say in the some circular orbit, there is one satellite here A and another satellite B is here, okay, and you want to catch this satellite. So, basically docking is required. So, and the orbit has to remain the same. So, what we will do that as it is moving from this place to this place, so it comes to point C. So, send it in some faster orbit, so that it goes and meets here. So, initial velocity vector is here V A, and we need to give a impulse here, so that the velocity becomes tangent to this orbit. So, velocity will be here in this direction V A prime. So, this is the necessary impulse then delta V A, and similarly here the velocity vector at C is V C, and this is going here in this direction V C prime. okay, or we can say that V c is the velocity here. So, V c prime is the change. So, V c prime minus V c, this is delta V c is the impulse required here in this place. Okay. Then thereby this satellite will be transferred from this place to the satellite B position. So, B will, by the time it will move from this position to this position, and the same time it has to, A has to move from here to the C. Okay. So, two impulse, one impulse is required here, okay, and one impulse is required here. So, minimum two impulse these are required. Okay. So, depending on the your requirement and which parameter or the this element or vital element you are trying to affect. So, thereby you are trying to affect here, in this case you are trying to affect theta. Okay. This is circular orbit. Okay. So, you are just trying to affect here, in this case the true anomaly can be measured from any point, but if it is circular orbit and both the satellites are in the same orbit. So, their angle will be maintained all the time, this angle from here to here, this will always be maintained. So, we have to gap this angle and catch it. So, for catching it, this is the strategy. Okay. So, we have seen that by doing this we can affect theta. Similarly, A, E, I, etcetera, all these things can be changed, and this is not a very big problem. Whatever we have covered already, using all those concepts, we will be able to do it. So, some historical details and other things I will supply you in the write up that I am providing. We will go for more of the technical issues. Classification of trajectory transfer. So, we can classify into different category. One is based on the center of force, the other one is based on number of impulses required. Transfer between orbits with the same center of force. This is what we are discussing here. Yes, the center remains same and you are transferring either from this point to this point, okay, or it can be in another orbit. You want to set up another orbit, say rather than you have to catch up, you just have to establish another orbit like this. So, this can be another case, but here the center of force that remains same. Okay. So, transfer between orbits with the same center of force, and another will be interplanetary or like you are going to the moon. So, this is transfer from one center of force to another center of force. So, transfer number of impulses. So, minimum one impulse required. So, one impulse, this is the minimum, two impulse, see multiple or three onwards, two impulses, multiple impulses, and then the continuous thrusting. Okay, so, we have all these cases. So, impulse means you are at one point you are giving change in velocity delta v. Okay, so, at two different points you are giving impulses delta v 1 and delta v 2. So, rocket is fired, the onboard rocket on the satellite. So, if you have this satellite, so onboard rocket is there. So, this is fired for a short duration, and the exhaust, this will provide the necessary thrust, and this equation is governed by the rocket equation for this. If it is in the space where atmosphere is not there, so simply we can write m dv equal to minus v times dm, where v is the exhaust velocity with respect to the satellite. And this can be derived. This is simple to derive it. And remember, here the quantity already we have put a sign here minus, and v is a positive quantity here, though it is in a opposite direction, and this is with respect to the satellite. So, this is not the absolute velocity, this is relative velocity, and this is the velocity that you will be knowing, the exhaust velocity, and generally it is available to you. Okay, and it depends on the construction of this satellite, this nozzle and your thrusting system. So, I will just do the derivation. Before that, let us complete this part. So, if this equation is given, so you can take this to be the rocket equation or the thruster equation in space. In atmosphere, this will get modified by the ambient pressure and the exhaust pressure. So, in that case we are not taking into account here. Okay, so, if I try to integrate it, so dm by m with minus sign here, we can write this as, and v multiplied by v equal to dv, and once we integrate, we can write delta v equal to v times ln m a divided by m b. So, you are starting your thrusting, or simply a or b, we can write 1 and 2. M 0 divided by m. M 0 is the initial mass and m is the final mass, where m equal to m 0 minus the burning rate, either plus or minus sign, whichever you want to use, we can use it. So, let us say the burning rate I indicated by W dot, okay, times T, and therefore, from here we will have minus, or dm by dt will be equal to minus dw by dt. Okay, so, you can see that if your initial mass of the satellite was 1000 kg, and after thrusting for some time, you are getting, say, some 10 kg of the fuel is burned. So, 990, and this is logarithmic pace, this is the exhaust velocity given to you. So, this is the impulse provided. So, wherever whatever the impulse is required, so if we know this quantity delta v, v is known to us and m 0 is known to us, and therefore, m can be calculated, and once m is calculated, so the amount of fuel burned will be m 0 minus m. So, this is the amount of fuel burned. So, for completing the maneuver, suppose you want to keep your satellite in the orbit for 10 years. Okay. So, during 10 years time, satellite will not remain in the same orbit, as we have done the things in the general perturbation method. Okay. So, it is not going to remain in the same orbit, it will keep changing over a period of time. So, if it changes, then we need to thrust it and put it back into the same orbit. So, periodically this orbit maintenance will be done, and in that periodic maintenance. So, say you are doing periodic maintenance after 1 month. Okay. So, after 1 month, how much fuel is required propulsion for your propulsion system, how much the propulsive liquid or the solid it is required, that can be computed, okay, using this equation. So, for one maneuver this is the requirement. Okay. Thereafter, your weight will reduce, the satellite mass will be different. So, that will act as your initial mass. So, if you are doing this maneuver after every 1 month, so you will be able to compute how much the fuel will be burned. So, this is an iterative process of designing the satellite. So, in the beginning you need to assemble all the components, okay, and you are not aware even about the inertia of the satellite. So, those things are computed. So, many methods of doing it, the theoretically also can be done on the CATIA, you can do it, or using your this experimental method, this can be done. Okay. So, once you know that these are the things going into the satellite, so you can approximately guess that what will be the weight of the satellite, okay. And from there then you can start designing. So, if this is the weight of the satellite, if I put this much of how much propellant will be required. Now, for housing that propellant, the propellant covering will be required, okay. That propulsion system, the whole propulsion system in which you are putting the propellant or the fuel. So, that has to be added to the satellite mass. So, it is not one shot process, nobody can do in one shot. So, it is iterative process, it is done iteratively, and as you refine, so you get more and more precise. So, after few iteration using computer, you will see that you are getting the nice result, it converges. So, for as many maneuvers you require, that many maneuver you can plan. So, depending on the propellant, your satellite life depends. Okay. Once the propellant is lost, so satellite will start deviating from the desired orbit, and thereafter it gets lost. Okay. So, this whole process therefore needs to be properly planned and coded on a computer, and once this has been done, then finally after the launch, once it is injected in the orbit, you will see that almost it follows the whatever you have planned, because in the space most of the things are already defined. What will be the effect of the planets or the earth or the sun or the moon, whatever, all those things are known. Okay. So, over a period of time, how much your orbit will deviate, that you will be knowing, okay. And once you know that, so everything can be worked out. But however, we do not have that much of time to go into each and every details of all these things, but with the basics that I will cover, you will be able to work out this issue. So, quickly I will wind up the rocket equation. Say the initial mass of the rocket is m and v is the velocity, and this we take as the e cap direction, positive direction. Okay, and thereafter out of this a small mass d w is burnt out, and this is the then the mass of the rocket, and its velocity becomes v plus delta v, and this delta w, this is thrown out with a absolute velocity v a, okay, and this is the weight delta w. So, because of this gets the reactive force here in this direction. So, we directly cannot apply the Newton's law, and therefore, we go through the conservation of linear momentum equation. So, we have m minus d w times v plus dv, okay, and the momentum of this part. So, this is dw, and then the momentum of this has to be added. So, v absolute is given. So, v absolute of this dw v a, and this must be equal to the initial momentum. Now, v a is the absolute velocity of this, and the absolute velocity equation we can write as, see here we can show it like this. With respect to this, the rocket v is the exhaust velocity. Okay, rocket itself is moving here in this direction with velocity v. Okay. So, if I impose a velocity minus v here in this direction, so this rocket becomes stationary. Okay. Then, with respect to the inertial space, what will be the exhaust velocity? So, this will be given by v minus v, and here in this direction, and this is your v a. So, this we can insert here in this place and expand it also, dw this we write as v plus delta v, and e cap direction, here in this e cap direction we are taking here, and plus delta w and v a, as we have written here, this is v minus v. So, this also we change here itself, v we have shown here in this direction. So, this is v minus v times e cap, minus v is here in this direction. So, we can write it this way with a minus sign. Okay. So, v minus v times e cap with a minus sign times m v times e cap. So, this is the initial velocity. So, here the way we have written, it is I could have also written as v a times e cap with a minus sign here in this place, and then v a simply replacing it by v minus v. Now, expand it. So, you can see that we can remove this, only this quantity remains, v plus delta v plus dw v minus v, and here this will come with a minus sign m v. Now, if m 0 is the initial mass, m is the mass at any time. So, this indicates or w is the mass burned. So, this is a positive quantity w we are taking. So, the mass later on it becomes m, and once we differentiate this, we can see that dw will be equal to dm. So, dw can be replaced by minus dm. So, this becomes plus v plus delta v, and this becomes plus dm times v minus v m v. Expand it, m v plus m delta v plus dm v plus dm times delta v plus dm times v minus dm v equal to m v. This cancels out, and then minus dm v this drops out. This is the quantity which is of second order. So, this is nearly 0, okay, as compared to the other terms. So, therefore, we drop them out, drop this term, okay, and we get here v delta v equal to minus v times this is delta m. Here we should have written delta W here in all the places. It is okay, delta W or dW directly, whatever you want to write, it is okay. Okay, so V times delta m, and if you write the same thing in the once the delta t tends to 0. So, we can write in terms of m dV equal to minus V times dm, and this is the equation which leads you to delta V equal to V 2 minus V 1 equal to V times ln m 1 by m 2. So, this is the thrusting equation. So, we stop here, and in the next lecture we will continue.